Come on. Okay. One thing that I noticed when I was looking at the class roster in my labs was that there were a handful of people who whose temporary access has expired. So at that point, then it's necessary to purchase access to continue. And in some cases, that temporary access had expired some days ago. So I know I've had it happen most semesters where somebody has a problem where like um, they have to wait to purchase access because they're waiting on financial aid, something like that. So I understand that sort of thing happens. So if you're in that position and it's getting to the point where homework due dates may be missed, I urge you to let me know what's going on. Um, and it's in a situation like that where you're waiting on something, so it's through no fault of your own that you're held up in doing the work. Please let me know, and I will certainly be accommodating in that kind of situation. But again, I need to hear from you if you're in that boat. Okay, let's see how many people. Okay, we have 12 people. All right, I think we'll make do with that. Now, we just have a couple of sections left on of new material to cover, so 1.8 and 1.9. So in a little less than 2 weeks, so 2 weeks from this past Monday, the first test will be posted. So I will be composing the test sometime over the next few days, or it might be like on the weekend, and put out a practice test. And so I'll cover section 1.8 today, 1.9 on Monday, and then Wednesday's class 1 week from today. That'll just be a review. So I'll be talking about the practice test during that time. Okay. Let's get the old screen share going. Okay. Now, so the point of these last two sections is to acquaint you with the concept of a linear transformation. And the easiest way to think of a linear transformation is it's essentially a matrix vector product. And in fact, a matrix vector product literally is a linear transformation. Those linear transformations that are not really defined as matrix vector products can still be viewed in that way in some sense. And that's something we'll get to in the next section. So since these two sections are all about linear transformations, here's the definition right here. So we have some function of n variables. So we have n variables as inputs, and then we have m variables as outputs. And there's no particular relationship between n and m. They might be equal, or either one could be less than or greater than the other. So a function that takes this vector space of dimension n to this space of dimension m is linear if it satisfies these properties. That you apply the transformation to a sum, it's just the sum of the transformation applied to x and y individually. Also, if you scale a vector x and apply the transformation to it, that's the same. Oops, typo. That should be x right here. All right. So it doesn't matter whether you multiply x by the constant and then apply the transform, or apply the transform and then multiply the constant. The result is the same. So basically, constant factors can be pulled out. Okay. Now, I'm going to add some linear transformations, and also describe some functions that are non-linear, so you can see the difference. So I'll just make up some examples here. So something like a function of one variable, f of x is 3x, that is linear. I'll make up a function of two variables. Okay, so that is linear. So here, so both cases, the number of outputs is only one. The output of both of these is just a number. But here, the number of inputs is one, so n is one. Whereas here we have two inputs. So we're going from R2 to just R. I'll do another that is as a vector valued output. So here we have 3 inputs. And I'll use the angle brackets to indicate a vector quantity. Okay. Right. Let's see. All right. So here we have an example of a function that's 3 inputs x, y, z, 3 outputs, which are the components of this vector, and here we have these 3 component functions that are all linear functions of x, y, and z. So those are all linear. Something that functions that are not linear transformations. Here's one it almost is. This is a quick modification of the last one. All right. That's not a linear transformation. Now, this might seem contradictory. You've probably been taught that this is a linear function, or maybe called that just because the graph of this function is a line. But it does not meet this definition, because if I plug x plus y into here, I can't do 3x plus 5 and 3y plus 5 added together and get the same result. So this is actually what is called, technically it's not a linear function. It's called an affine function. Right. So it's a linear function with a shift of a plus 5. So this is not fall into this category. Other examples that would be more obvious as nonlinear, like all right. So if I have something like that, that is nonlinear. And one more. Okay. I want 2 variables in this one. So this one, the power of x and power of y are both 1, but they're multiplied together. That makes it nonlinear. Now, because there are 2 variables, there is a term for this. It's bilinear. Because it's a function of, it's a linear function of just x or linear function of just y, but not a linear function of both. In other words, if I hold y fixed, this is a linear function of x. If I hold x fixed, it's a linear function of y. But it's not a linear function of x and y. It does not meet this definition. If I had more than 2 variables, then like if I had x, y, z, then that would be a multilinear function. But all of these do not fit this definition. So it's something like this, where basically you're taking your input variables, you're multiplying them by scalars, just numbers, and adding them up. That's when it's linear. So even adding a constant, it's not. Right. So anytime you have a vector x in a matrix A, that defines a linear transformation. So the input is x, and then the output is the matrix vector product ax. So to understand linear transformations, it's helpful to understand matrix vector products. So they're not exactly the same thing, but they almost are. So in fact, every linear transformation can be described using a matrix. That's something we'll get to next section. Now, an important term, if I take a vector x and I plug it into a linear transformation T, the result of that is called the image. So x is the input, T of x, the output, is also called the image. Since there's certain homework problems that ask for the image of some vector. All right. So that's today's jargon. Now, so for this problem, we have a linear transformation defined to be this product. So whatever x vector is coming in, we're just multiplying it by the matrix A. And that means multiplying each column by the elements of x and adding them up. So what it's asking for here is find a vector x whose image under T is B. So in other words, it's finding a vector x so that A times x is equal to B. And then if we can, once we find such a vector x, then the next question is that vector unique? Is it the only one whose image is B? So what do we actually have to do to answer this question? So we want to find x so that A times x is B. So we want to solve this system of equations. This class is kind of funny in a way because you learn at the beginning, here's how you solve a system of linear equations. And then you discover so many different ways, phrasing problems that all boil down to asking you to solve a system of linear equations. Finding a vector x whose image under its transformation is B, we're still solving it, this kind of linear system. So you're doing the same thing as you have been from the beginning, that you're performing row operations on this augmented matrix. So we take A and B and put them together. Okay. So then we're going to row reduce this, and if we find that the system is consistent, then we'll know that there is a vector x whose image is B, and we'll also be able to solve for it. So then we go through the usual process, as we've seen ad nauseum, that we're multiplying this row by 4 and subtracting it from this row to eliminate this 4 down here. Okay. And then we see, okay, we just add these two rows together to eliminate this -1 down here. And we see that these rows are not parallel to one another. Like this row is definitely not a scalar multiple of this one. So the system will turn out to be consistent. We can tell that before we go any further. Okay. All right. Okay. All right. So then, so now we see that the system is consistent, and we go ahead and solve for it. So we have this system of equations to solve, and we need to solve for x3, x2, and x1 by working with these equations starting from the bottom and working our way up. So this is back substitution that we carry out. So to have a routine down for that, because you don't want to go through the trouble of writing it as a system of equations. So actually, I'll have all this visible on one page. Okay, so here's the matrix we're dealing with. So starting with this equation, this is our right-hand side. So we divide this element by this one to get x3. Then we move up to this equation. So the routine is, we're solving for x2. So any terms we have to the right of this element, we need to negate these coefficients because we're moving them to the other side. So I'm having minus 12 minus the minus 2 times x3. Why x3? We're in the third column. And then, because the coefficient of x2 is 1, that's what we're dividing by. So then we can go ahead and work all this out. We're taking a value of x3 and substituting it in here. And then we get minus 14. Now, these two values will be substituted into this first equation where we go after x1. So here too, we have minus 4 as our right-hand side value. So that always goes first. Then we're taking these coefficients and we're subtracting them. We're moving into the other terms to the other side, times x2 for this one and x3 for this one. So right-hand side value, negate other coefficients, substitute in your values that we got before, and then we end up with this. So here's our solution. So minus 1, minus 14, minus 56 for x3, x2, and x1. So then we put those in a vector, and that is the solution that we have. All right. Questions about how that was arrived at? This process is followed quite frequently. So I'm going to put a note here. Okay. So you're in a situation where you're solving this linear equation, where you have these coefficients. Let's see. All right. So all these linear equations that you're solving have this form, and you're trying to solve this equation for xi, and these other x's are already known, so ones of a higher index. But really what you're working with is not an equation that's written like this. It might be easier, but it's more concise to be working with a matrix. So really what you have is all right. So yeah, you'll have some zeros most likely, except for in the first row. Okay, and then you have the coefficient of what you're trying to solve for. And then you have more coefficients until the last one. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I need a couple more of these. Okay. And then you have this right-hand side value over here. So this is what you're actually working with, or several rows like this. All right. So and just from rearranging, we have, as I was saying earlier, we're working through the example. Right-hand side value first, and then the negatives of all of these with the corresponding x values substituted in. So then you work out all that. And then if there's a coefficient here other than 1, then that's what you're dividing by. So, so this is the formula for each x based on the row of a matrix that you're working with as you go through rows from bottom to top. All right. So now we have an x whose image under this transformation gives us b. But now there's a matter of, is that the only x? And it turns out that that is a quick question to answer. The answer is yes, it is unique. Why? Because there's a pivot position in every column. Another way of, there are not any free variables. If there were any free variables, then we would have infinitely many solutions. Okay. Next, we have a similar problem. So here's our transformation. It's multiplying by this matrix A to try to get this vector B. So is there an x that would do that? So, so if there is such an x, it would have 3 elements because there are 3 columns in the matrix. So once again, you work with the augmented matrix just by throwing in this column on the right. And then we have just one row operation to perform, thankfully, because we only have 2 rows. So what would that be?
Row 2 plus 2 row 1.
Yes, that'll do it. Because the ratio here is -2, so it gets subtracted. So twice row 1 plus row 2 will eliminate that element.
Wouldn't x3 be a free variable though?
Yes, we are going to have a free variable.
Okay.
Yeah. Yeah, because we only have 2 rows, so you can have at most 2 pivot positions. But we have 3 columns in the matrix, so yes, there will be a free variable. Now, for convenience, notice is not required, but it makes things easier later. Every element here is a multiple of 6. I'm going to divide the second row by -6, just to make the numbers a little nicer. So now, this is a system of equations that we're dealing with. It's consistent. Now, So you know it's consistent at least because you have a pivot position in every row. So I'll make a note of that. If there's a pivot position in every row, then a solution exists. Pivot position in every column means if a solution exists, then it is unique. So things that you can tell very quickly about a system once you've reduced it. And I have to say, if a solution exists, because what if you have a matrix that has only a few columns and many rows? Then you may have a pivot position in every column, but it's possible that the system might be inconsistent. Okay, so here we have a pivot position in every row, these two spots. So a solution does exist, but because we have this excess column here, as was just mentioned, we do have a free variable x3. So you could choose x3 to be anything. That's what it means to be a free variable, and then solve for x2 and x1 using back substitution. So to get a solution, we'll just set x3 equal to 0. So then we go through the same process. Okay. So here I have a right-hand side value of 1, subtracting this off. But then the x3 is 0, so we're just going to get 1 in that case. Then we go up to x1. So here, right-hand side value. Throw these two terms onto the other side. Well, if they're unknowns x2 and x3. Substitute, so 0 here, 1 here. Well, here I've cleaned this up a little bit, but yeah, now we go ahead and substitute, and we're only going to get this term here. So we have 3 as a result. So we do have a solution. So 3 and 1 from our basic variables, and then our free variable x3 is 0. So the image under this transformation of x, this x, is in fact a b that we were given. But because of a free variable, it is not unique. So I could substitute in any value at all for x3, and then solve for x1 and x2 in terms of it, and the image will still be equal to b. Questions on these two that are closely related? All right. Okay. Now, here, instead of trying to find x where the image is equal to a specific given vector b, like in these problems, trying to see which vectors x have an image of where the image is equal to 0. Now, here's another way of writing a linear transformation. So the input is x, the output is ax. So we want to find x so that ax is 0 for this matrix A. Okay, so we go through the same process, and not much to do in terms of row operations. We're looking at a ratio of 2. Whoops. All right. Now, so here we've finished off the first column already. Here we're going to take twice this row and subtract it from here. And but one thing you can tell right off the bat is the second row is twice the first row. So you can tell before you even do it, it's going to wipe it out. So here we have 3 rows, 4 columns. We only have 2 pivot positions. So what you can tell right off the bat is you're going to have free variables. You're going to have 2 of them, x3 and x4, because we have pivot positions in these 2 columns, the first and second. So we have infinitely many solutions to this system. Okay, instead of just a trivial solution. So we could pick x3 and x4 to be anything, and then solve for x1 and x2. So what we're going to do is we're just going to leave x3 and x4 as variables. We're not going to assign values to them, and then get formulas for x1 and x2 in terms of these. So first for x2. So take these coefficients, negate them. Our right-hand side is 0, so we're not going to have anything there. And then that's it, because the coefficient of this is 1. We don't have to do anything further. So that's our formula for x2 in terms of x3 and x4. For x1, same idea. Our right-hand side is 0. We negate all of these coefficients to get 4, minus 13, and 6. But now there's one more thing to do. We want to express x1 in terms of only x3 and x4, but we have this x2 here. That's fine. We go ahead and substitute this in there. Okay, there you go. And then we just grind it out and combine all the like terms and wind up with that. So then, if you want to describe all possible solutions, there's going to be 2 vectors involved. Why? Because you have 2 free variables. So, okay, I'm gonna move this onto its own page. Okay, so first you have a vector that has all multiples of x3 from your formulas. So notice in x1 we have 7x3, so we put a 7 there. x2 we have a 5, so that goes there. x3, its own spot would be 1. There is no x4, so it would be 0. And then you do the same thing for all the multiples of x4 that you see in your formulas. Okay. Yeah, so minus 6 from x1, minus 3 from x2, nothing for x3, and then x4. It's a 1. So this describes all possible solutions of ax equals 0. So the image of any vector of this type for whatever values of x3 and x4 you substitute in will be 0. Okay. Now this problem is somewhat similar to the first 2, where you're given a matrix A that describes a linear transformation. You're given a specific vector B, and you're trying to find out is Ax equal to B. Now the only difference between these 2 problems and the first 2, there you were told there is a vector X that whose image is B. You're not assured of that in this case. You might conclude that there's no solution, but you won't find out until you carry out the row reduction. Okay, so if vector B is in the range of this transformation, I think in terms of like the domain and range of a function, another way of putting it is B is in the range of this matrix, and that is true if and only if AX equals B has a solution. So basically trying to determine if the system AX equals B is consistent. So we go ahead and form the augmented matrix from these two. Okay. And then you're going to carry out the row reduction. And it's nice of my labs to put a 0 in there to have one less row operation to carry out. So it's going to, oh, there's a typo there. That should be a subscript. So row 3 minus 3 times row 1. It's also convenient that they have a 1 up here, so it makes it easy to see what row operation to perform. Okay, so then our matrix after carrying that out is this. Notice that as we look at the rows that remain, rows 2 and 3, here you double these elements and you get these, except here. So these rows are not scalar multiples of one another. So when we carry out the next row operation, we're going to find a, we're not going to get a row of zeros. Okay, so here in this matrix of 4 columns, we have pivot positions in every row. In the first column, second column, fourth column. X3 is a free variable. But because we have a pivot position in every row, the system is consistent. So B is in the range of linear transformation. In this case, it's, you're not required to come up with a vector x whose image is B. If you did have to, you'd have this free variable x3, and you could solve for really x4 would just be 0, and then you could solve for x1 and x2 in terms of x3. Here it's the same idea. We're going to form the augmented matrix from these two. All right, so I'll just put that together. Okay, and now again we carry out the row operations, which thanks to this 1 up here, as you see which multiples of a first row we need to eliminate these elements down here. And we see what happens. Okay, so here we just subtract these rows to cancel out this 0 here. Okay, and then add twice this row to this one to cancel out that one. Okay. Now, at this point, if we continue, we would use this element to eliminate these two down below. Can anyone tell me what I ought to do instead just to make the numbers easier to work with?
On row 2, can you divide by 3? Because all of them are multiple of 3.
Actually, that is
or negative 3.
Actually, that would work. Yeah, because they're divisible by 3, you could do that.
Or swap row 3 and row 2.
Yes, that is. Yeah, so either one would work because either way you're going to get a 1 up here.
Okay.
So both good ideas. Unfortunately for convenience, I got to go for one that's in my notes. So I did the row swap. Okay. And what happens in that case? Okay, so now we have a 1 up here. And then, yeah, then it's easy to get your multipliers. So -3 in this case and 7 in this case to operate on these rows. All right, and sure enough, because here you multiply these by -3 and you get -3 and -6. Those two elements get wiped out, and this is the only one that's left. And then same thing's going to happen here. Like we have 1 times 7 is 7, 2 times 7 is 14. So those will be wiped out too. Okay. And now we just have these last ones to work on. And then actually, I'll go ahead and divide that third row by 3. Just to make that 1, 1. And then just need to work on this row and add 18 times the third row to the fourth row. And then we're done. So the matrix is finally in echelon, echelon form. But here's the problem. This is an augmented matrix. So within this coefficient matrix, we have a row that turned out to be entirely zeros, and we have something non-zero over here. So the conclusion is that this system is inconsistent. So only if this fourth element had turned out to be 0 would we actually have a solution. But here we don't. And as I mentioned, if you have a pivot position in every row, then a solution exists. But we do not have that here. We only have pivot positions in rows 1, 2, and 3, not in the fourth row. So when it happens, it just depends. A solution might still exist, but not here. It depends on the right-hand side. Now, this next one, these vectors, E1 and E2, are of particular importance. They actually come up very often in various situations, contexts in linear algebra, where the vector EJ is defined by having all elements 0, except whatever index we have here, that element is a 1. These are similar to, like, especially if you have a physics background. In physics, you come across the vectors I and J in 2 dimensions, or I, J, K in 3 dimensions. It's these vectors, but in a linear algebra setting, they're known as E1, E2, and so on. They're also the columns of the identity matrix, which we'll come across later. So here we have these 2 vectors, E1 and E2, and then these vectors Y1 and Y2. And all of these vectors are used to define this linear transformation T. So T times E1 gives you Y1, and T applied to E2 gives you Y2. So what the question is asking is, if we know this much about the linear transformation, then what happens if we plug in this given vector here, 5 and -4, or any vector, x1, x2? It'd be nice to use this information to get a formula of linear transformation for whatever vector we plug into it. So what we'll do is we'll actually use the properties of a linear transformation that are given here. So I'm going to be making heavy use of these to work out this problem. All right, let's get this onto a new page. All right, so we want the image of 5 minus 4. So it's a bit of a mess. It'll come clear in a second. Okay. So what I've done is I've expressed 5 minus 4 in terms of these vectors, E1 and E2. And it's very easy to do because of the structure of these vectors. All zeros in every element except for one of them is a 1. So the coefficient of E1 is the first element. The coefficient of E2 is the second element. So then I can write this as 5E1 minus 4E2. Now, now I use the properties of T as a linear transformation. Because, actually, I'm going to put an intermediate step in here. All right. So this is the same thing as saying this is T of 5E1 minus T of 4E2. Okay. So here, transformation of a difference is equal to the difference of a transformations. Okay. Then in each of these terms, I have these constants, 5 and 4. Pull them out. So now I've expressed T of this vector in terms of T applied to E1 and E2. But I know what those are from what's given. E1 maps to Y1, E2 maps to Y2. So now I can fill those in place of T of E1 and T of E2. And now I fill in what those vectors are. All right, so here's Y1 and here's Y2. And then oops, okay. So now I'm just carrying out the algebra from this point, multiplying this vector by 5, multiplying this vector by 4. Okay. And then I get a result of 19 and 3. So 19, 3 is the image of this vector 5 and minus 4. So it's using the properties of a linear transformation and what it maps the vectors E1 and E2 into. So now I want to do the same thing, except instead of having a specific vector 5 minus 4, I want an image of a generic vector x1 and x2. So if I carry out that process, okay, same idea, that this is x1 times E1 plus x2 times E2. And then again, I can use the properties of a linear transformation where I break this up into separate terms, T applied to each one, pull out the scaling factors, x1 and x2, and then I fill in what T of E1 and T of E2 are. That's Y1 and Y2 again. So now I can fill in those vectors. And like before, I can just distribute the x1 to here and x2 to here and come out of it with a single vector. Okay. And then just, and this is that vector. So for any x that I'm given with components x1 and x2, this is my formula. for t of x. So this fully describes my linear transformation. So if you have a linear transformation of n variables, in this case n is 2, and you know what the linear transformation does to e1, e2, and so on up to en, then through a process like this, you can describe the entire linear transformation. But I want to point out something. Here, y1 and y2, look at the coefficients. So here, the coefficients of x1 are just y1. Coefficients of x2 are just y2. So these, I can just take these vectors and put them together, and that alone describes my whole linear transformation as a function of x. All right. Now, in this next one, we have a description of linear transformation, that whatever x that comes in, it's mapped to this vector. So x1 times v1 plus x2 times v2. So we want to describe this using a matrix. Now it turns out this can be answered very quickly, but I want to show you how that answer is obtained so that you see why you can do it that quickly when you have a similar problem. Okay. All right, so here is my formula for t of x. So it's given by this. Okay. Wait, I need a new page again. So here I have this written out, so now I'll just fill in v1 and v2. Okay. So now I can go ahead and distribute x1 and x2 to these vectors and form one vector. Okay. So this is a formula for my linear transformation, but I want to write this as a matrix times the vector x. But the way I can do that is just by taking a coefficient. So -5 and 8 give me the first column. -8, -4 give me the second column. So it's these vectors. I can just read the matrix off of these columns. That's when you see it all worked out. All right, so the linear transformation is a times x, where a is this matrix. So anytime you're given a linear transformation, of this form, where in terms of the components of x, then whatever vectors you're multiplying them by, those are the columns of this matrix A. So you can just jump straight to that step and be done with it. So anytime you have an expression like this, it's linear. or several expressions like this stacked into a vector. If you group them, basically so that you can have your x's all lined up, you can see, okay, the coefficients of x1, that's a column. Coefficients of x2, that's a column, and however many variables you have. So that's how you can interpret this vector as a matrix vector product. All right, last problem. Once again, we want to know if this vector is in the range of this linear transformation. And in terms of row operations, it's a bit of a doozy. So once again, we want to see if ax equals b has a solution. So if a system is found to be consistent, then we want to go ahead and solve it, at least obtain a solution x. There might be infinitely many, but we want the problem requires you to find one. So as before, we work with the augmented matrix. And what ends up happening in this case is bound to happen sometime. The numbers don't work out nicely. You can't tell. We don't have a 1 anywhere here. And these numbers are not all divisible by one another. So here we're taking 9/4 times this row and adding it, the first row and adding it to the second. Okay. And we see that things get ugly. Now, what you can do to get rid of these annoying denominators, here we have a common denominator of 4, and you can multiply by that. And but first, I want to get rid of all the elements in the first column that need to be eliminated. Okay. And finally, this one. Okay. All right, so here we have a bunch of fractions. And what I do is in each row, I multiply by the common denominator. Thankfully, it's just 2 or 4 to at least have integers here. So things aren't quite as nasty. But, well, actually, that does turn out to be enough. Well, okay, it's not entirely fraction free. At least I can continue the row operation. So, for example, I can subtract these next 2 rows to continue the row reduction process. Okay, but unfortunately, there's more fractionness here, and this is why we have programs like MATLAB, which I actually use in preparing a lot of the notes to handle these kind of things to make sure there are no mistakes. And MATLAB is accessible to all USM students now. Okay, so then we're taking care of a second column. Here again, we have a need to get rid of fractions. So I'd like to have 1s in these left positions. And notice we have 2 rows that are identical. So sure enough, once we do one more row operation, we're going to get a row of zeros. Okay. But thankfully, this row turned out to be all zeros, as opposed to a previous problem where we had this is an augmented matrix again, where this part was all zeros. We had something non-zero here. That would be an inconsistent system. But this system is consistent. So B is in the range of a linear transformation. And now we know it's possible, at least, to find an x so that AX is equal to B. We have pivot positions here, here, here. So X4 does not have a pivot position. So there's no pivot position in the 4th column. Therefore, it's a free variable. Okay. So what we'll do is it's just looking for a solution. So we just set x4 equal to 0, and then we can solve for everything else. So we just deal with this final matrix here. Okay, so we're going to solve for x3, but that's just going to be equal to 1. And then we can go ahead and solve for x2, right-hand side value, throw these terms on the other side, so negate the coefficients. And we're going to divide by 10 because of this coefficient of 10 here. We just need to substitute in our values for x3 is 1 and x4 is 0. So look at that, the number's working out nicely. And finally, x1, we have our right-hand side value of 7. Negate all these. Substitute in x2, x3, and then x4 is 0. And we get that as a result. So now we have our solution. X4 of 3 variables set to 0, and our other values, 5, 8, and 1, make up the solution. But we could have set x4 to anything and gotten a infinite many solutions. Yes.
Can you go back? Not.
Oh, where?
To the conclusion.
Oh, here?
No, further. That's it.
Okay. Yeah, we're just finding these in reverse order. Other questions? Okay. I will end the recording at this point. Anyone who has questions can stick around. All others can go.